Hello and welcome to another episode of Maths with Mrs. Banks, where we make maths fun and easy to learn. And in this video, we're going to focus on part 2 of a 5-part video series on trigonometry for mathematics grade 11. And this part, which is video number 2, will be focusing on the reduction angle formulae. On that note, please don't forget to click the subscribe button so you don't miss out on video 3, 4, and 5 in this series, and more videos will upload in the future. We have a lot to cover, so let's start. In summary, we're going to look at special angles, the quotient identity, and the square identity, understand what they are and how you use them in reduction angle formulae. Number 2, we're going to look at the reduction angle formulae and how to go about understanding how to use them in a question. Number 3, we're going to look at how to simplify without using a calculator and the tools that you need in order to be able to do that without any problems. And lastly, number 4, we're going to look at how to prove trigonometric identities. Now, you will see as we go towards the end that all the basics that we're going to cover in this video and the video that we started with in this series, video number 1, will all give you the tools to be able to handle questions relating to how to simplify without using a calculator without any issues or problems. Let's start. Special angles come in two triangles. The first one is the 30, 60, 90 degrees, and the second one is the 45, 45, 90 degrees. Both of these are obviously right angle triangles. One is isosceles. This is the isosceles one, where you've got two angles that are equal and two sides corresponding to those. And then you've got the scaling one, which is the 30, 60, and 90 degrees. These two triangles will be provided to you in the formula sheet in a final exam or any test that you write. However, it will be beneficial for you to learn how to reproduce these triangles. Now let me take you through how you use these triangles to calculate anything. Let's say, for example, they say to you calculate the tangent of 60 degrees without using a calculator. We know that the trigonometric ratio 10 is opposite over hypotenuse. No, so it's opposite over adjacent, which is in short y over x. And according to this triangle, so what you do is you look for the triangle with the angle that you're trying to calculate without using a calculator, and that triangle will be the 30, 60 degrees, in this case 90 degrees. You will then locate the angle so that it can become your angle of focus, and now from the angle you look at what this side opposite it and the side adjacent to it are. So we go the side opposite the angle 60 degrees in this triangle is square root of 3 over the side adjacent, which is 1, and that gives us simply the square root of 3. That's the answer, and that's how you do that without a calculator. Now let's look at special identities. We've got two special identities that we're going to focus on in this video. The first one is the quotient identity, which is how we write the tangent of theta in terms of sine theta over cos of theta. That's the first one. And then you've got the second one called the square identity, which basically tells you that it does not matter what angle you're looking for. If the square of the cos and the square of the sine of that angle added together, you will always get the answer of 1. Don't believe me? No problem. Let's take a look at that. Cos squared of, let's say, 30 degrees plus sine squared 30 degrees. Okay, let's calculate this using the triangle. Let's use the triangle. The cos of 30 degrees is equals to, here is the 30 degree angle. The cos is adjacent over hypotenuse, so that will be square root of 3 over 2. So that will be equals to the square root of 3 over 2, all squared, must be squared, plus, okay, and the sine here will be the sine of angle 30 is opposite over hypotenuse, so that's 1 over 2. That is also squared. Let's calculate that and see. All right, so that gives us 3 over 4 plus, next one is 1 over 4 as you can see for yourself, got a common denominator, so all we do is we add the two numerators together, and that gives us 4 over 4, which is 1, and that's how you prove it. So this is proven, and this is how you prove it. Now notice that from the square identity, you've got other derivatives. You can basically express the square identity in different ways that you like. Let's look at how you can use this to express in terms of sine or theta what you need to express, and this becomes very important, especially when you're looking at one specific type of simplifying without using a calculator, and that we're going to start with, and you'll see exactly how this is important. So meaning that you can express cos squared theta as equals to 1 minus sine squared theta, meaning that therefore from this you can then express the cos of theta as the square root of 1 minus sine squared theta. This is important because we're going to use this a lot. Similarly, you can also express sine squared theta in terms of cos. So sine squared theta can also be expressed as 1 minus cos squared theta, meaning that therefore sine of theta, if you take the square root of both sides, will leave you with the square root of 1 minus cos squared theta. So if you have a trigonometric ratio and they give you in one trigonometric ratio and they want you to express it in terms of the other, we're going to look at that specific example in a short while. This is how you then express the cos and the sine in terms of the other trigonometric ratio. As keep that in mind, because it's going to be very, very important to remember this. Nota bene, remember. Now let's look at how to reduce angle, the reduction angle formulae. This is what you need to use whenever you do not have a calculator, or they say to you simplify without a calculator. But first you need to understand how this was derived. How was it derived? Let's look at this shortly. All right, we're going to take that triangle of 30 degrees, 60 degrees, and use it to, okay, this is 30 degrees and that is 60. Root 3 is opposite 60 degrees, and then 1 is opposite the other one, and this 2 is the hypotenuse. All right, now if you take, we'll let theta equals to 30 degrees. Okay, let's start with that, and you will see how it works out. Now in the first quadrant, according to the cast diagram, okay, everything is positive. That's what the A stands for. That's what that means. All trigonometric ratios are positive here. In the second quadrant, only sine and its reciprocal, and you should know what the reciprocal of sine is by now. If you don't, please go back to the video number 1 to find that in a bit more detail than in this video. And in quadrant 3, you've got tan and its reciprocal that are positive. Everything else is negative. And then in the fourth quadrant, you've got the cos and its reciprocal positive, and everything else negative. The question is, how do we arrive at this quadrant? How do we express angles in a compound format that end us leading us to land in these quadrants in terms of our angles? You've got the 180 minus plus theta, or plus or minus theta, reduction angle formulae. You've got the 360 degrees plus or minus theta, and the negative theta, and then you've got the ones that I call the co-function ones, which are 90 degrees plus or minus theta. Let's start with these 180 plus or minus theta, 360 plus or minus theta, and minus theta, including multiples of 360 degrees. So it could be anything, negative 360 degrees plus or minus theta, or plus 360, or 2 times 360. It does not matter, as long as you make a revolution. Does not matter how many times you round off, you go back to exactly 0. So you will see how you still land at one place regardless of how many revolutions you go before you add a particular angle, which is theta, which is an acute angle. Now let's look at an example. 180 degrees plus or minus theta, 360 plus or minus theta, and minus theta. These just basically change sign depending on where they land and whether the trigonometric ratio in that quadrant it lands on is positive or negative. They don't change the trigonometric ratio. The second part though, this one's 90 degrees plus or minus theta, change into the cofunction. Let me show you. Okay, the sine of 30 degrees is found in the first quadrant, so we know that everyone is positive in the first quadrant, so sine will be positive there. All right, so that gives us what? According to this triangle, sine of 30 degrees is opposite over hypotenuse, that's 1 over 2. I'm gonna give you an example. What happens when we then go sine of 180 degrees minus 30? 180 minus 30 lands us in the second quadrant. This is how we express angles in the second quadrant. That's 180 degrees minus theta. In the first quadrant, we express them as theta, or 360 plus theta, or k times 360 plus theta. It does not matter how many revolutions. In the third quadrant, we express them as 180 degrees plus theta. And in the fourth quadrant, we express them as 360 degrees minus theta, or negative theta. Right, that's where you land in terms of quadrants. So any angle that can be expressed in terms of 180 minus theta, where theta is usually an acute angle, meaning an angle between 0 and 90 degrees, will land in the second quadrant. 180 plus theta will land in the third quadrant, and so on and so forth. You need to know how this works. Now let's see then, how does this translate into what we end up getting. Now let's look at 180 minus 30. Sine of 180 minus 30 lands us in the second quadrant. All right, let's see what value it gives us. Okay, so here we go. Sine of 180 minus 30. I just want to give you an example so you can see for yourself how this works. Sine of 180 minus 30. 180 minus 30. Okay, so that's sine of 180 minus 30. That gives us 1 over 2. It's exactly the same as the sine of 30 degrees, 1 over 2. Exactly the same as the sine of 30 degrees. So you can see for yourself. Sine is positive in the second quadrant if it falls in the second quadrant, which is where the angle 180 minus 30 degrees, which is actually 150 lands. Now, 180 plus 30 lands us in the third quadrant. There, let's see what happens to sine. 180 sine of 180 plus theta plus 30 degrees gives us negative 1 over 2, which makes sense according to the cast diagram, because it is negative there. Sine is negative here, and this is how you navigate the reduction angle formula. We can choose any one. For example, cos of 360 plus 30, that will land us back in the first quadrant, which will exactly be the same as the cos of 30. What is the cos of 30? Cos of 30 is adjacent over hypotenuse, which is the square root of 3 over 2. Let's calculate the cos of 360 plus 30 degrees, and you will see for yourself that indeed this is correct across the board. It lands us in the first quadrant, so it is positive. Same value as that of cos of theta, and positive because it is positive in that quadrant. Cos is positive in the first quadrant like all the other trigonometric ratio, and that's how basically you navigate the cast diagram when you're reducing angles. Now let's look at the last bit, which is, now notice that all of this change into exactly, the only thing that changes here is the sign. It can either be positive or negative. That's all that changes. Okay, don't believe me, let's look at 360 minus 30. Cos of 360 minus 30 lands us in the fourth quadrant, and cos is supposed to be positive there, and you will see it will indeed be positive. So that's cos of minus the there, square root of 3 over 2. Square root of 3 over 2, which is the same as cos of 30 degrees. Same, okay, which is also the same as cos of 30 degrees. I just wanted to prove that to you. You can see for yourself. Now let's look at what happens when you have 90 degrees plus or minus sine of theta. Now 90 degrees minus theta will land us in the first quadrant. Cool. meaning that all those signs will all be positive. It does not matter which one you're working with. However, please notice something, that it then, whenever you have 90 degrees, it changes into its cofunction. The cofunction of sine is cos, and the cofunction of sine is cos. Cos is simply short for cosine, so it changes into its cofunction. Right, what is cos of 90 degrees minus 30 degrees? It will be in the first quadrant. Let's see. Cos of 90 minus 30, and that is 1 over 2. 1 over 2 is the same as the sine of theta. 1 over 2 is the same as the sine of 30 degrees. Now let's look at what happens to the cos in the second quadrant, which is where 90 degrees plus theta lands us. 90 degrees plus theta lands us here, and then 90 degrees minus theta is in the first quadrant. What happens when we go cos of 90 degrees plus 30 instead of minus 30? It gives us minus 1 over 2, which is minus sine of theta. Negative 1 over 2, which is negative sine of theta. All right. Now notice that cos of 90 degrees plus theta is negative, and it turns into a negative sign, even though the sign in general originally is positive in the second quadrant. The reason why, whenever you're dealing with the 90 degree plus or minus or the cofunctions, right, we look at what original trigonometric ratio changes into the cofunction. If it's cos, we know that originally cos is negative in the second quadrant, and that's how you determine. Now, cos of 90 degrees, sine of 90 degrees plus 30 degrees will be a positive. Sine of 90 degrees plus 30 will be positive, because even though it will change into a cos, which is the cofunction of sine, the original trigonometric ratio of sine is positive in the second quadrant. That's why sine of 90 plus 30, you will see it gives us square root of 3 over 2, which is exactly the same thing as the cos of theta. Check 90 degrees minus 30. Sine of 90 degrees minus 30 will also give you the positive square root of 3 over 2, which is cos of 30 degrees. And that's how it all happens. So that is how you work out trigonometric ratios and reduction angle formulas with a cast diagram. If you don't get it yet, no sweat. We're going to look at practical examples, and you will see for yourself exactly how we navigate that in practice. Now, this is a summary of what changes, where the quadrant will falls, where, what angle, what compound angle you have there, and which trigonometric ratios are positive and which ones are negative. You can take a screenshot, post this, take a look at it, have it somewhere close to you, wherever you can draw onto it at any time, but just pause to read or find a way to reproduce this. Now we start with the questions. Now we look at how to simplify without using a calculator. The first type of question that comes and says let's simplify without a calculator is questions like this, where they say to you, if the sine of 17 degrees equals to a, without using a calculator, express the following in terms of a. All right, let's look at the first one, 5.2.1. We're given 10 of 17 degrees, and the information that is given to us is that of sine 17 and given to us in terms of a. All right, so what you do is, first of all, you use the square identity, the quotient identity. Remember, the quotient identity says that 10 of any angle theta can be reduced or changed into the sine of theta over the cos of theta. So here the theta is the 17 degrees. We already know what the sine of theta is. It's given to us. Now, to express cos of 17 in terms of the sine of theta, we use the square identity. The square identity becomes very important. Remember, the square identity says sine square of theta plus cos of square of theta equals to 1, meaning that therefore cos square of theta will be expressed as 1 minus sine square of theta, meaning that therefore the cos of theta will be equals to the square root of 1 minus sine square theta, and that's how you do it. Similarly, the sine of theta in terms of cos will be the square root of 1 minus cos square theta. So that becomes what? Sine of 17 degrees over 1 minus, the square root of 1 minus sine square theta. Okay, let me fix that. Sorry about it. 1 minus sine squared 17 degrees. You know what the sine of 17 degrees is? They give it to us. We can just replace that with an a. That gives us, therefore, we have a at the bottom, at the top, over the square root of 1 minus a squared. And that's how you navigate questions like this. That's how you navigate questions like this, using the square identity as your source identity to work through. Sine of 107, this is a compound angle, right? Whenever you have this, notice that this can be written as 90 degrees plus an acute angle. How do we find that acute angle? You just go to find the theta, you just go 107 minus 90 degrees. So these ones will be centered around 90 degrees. That's how you work them out. So 107 minus 90 degrees, it will give us the acute angle that we need to add into that, and that is 17 degrees. So that gives us 90 degrees plus 17 degrees, which we then use the cofunction reduction angle formulae to simplify. So sine of 90 degrees plus 70 degrees, it lands us in the second quadrant, right? And sine is positive there, right? So meaning that the cofunction that it changes into because of the 90 degree, which is cos, will also be positive. So that changes into cos of 17 degrees. We've already calculated cos of 17 degrees from the other. That will be equals to the square root of 1 minus sine squared of 17 degrees. We know what sine squared or sine of 17 degrees is. It's a, they gave it to us. So that will be simply the square root of 1 minus a squared. Lastly, cos squared of, okay, that will be equals to, okay, you get to work with the compound angles. All right, so you go 253, that is smaller than 270 degrees there. So it's in the third quadrant. It's bigger than 180. It's in the third quadrant. And we know that in the third quadrant, angles are expressed as 180 plus theta. So let's simply subtract 180 to see what the acute angle was added to that. So 253 minus 180. 253 minus 180. That will give you 73 degrees, and that's the acute angle that was added there. So that will be 180 plus 73 degrees. That's how you work it out. 180 plus 73 degrees. So that's 180 plus 73 degrees, all squared, plus the sine of, let's check it out, the sine of 557 is bigger than 360. So what you do is you see how many 360s you can subtract. Okay, so you can see how the whole angle was constructed. So we subtract 360. 557 minus 360, that's 360. Okay, now it's 197. Let's subtract 180. And that will give us the acute angle 17 degrees. So this can then be written as 360 plus 180 plus 17 degrees. And that's how we write it. 360 plus 180 plus 17 degrees. Okay, it's all squared. So we square it. Now we know that 360 means a revolution, so meaning that you go one revolution 360, so that will be 360 plus 180 plus 17. It lands us in the third quadrant where sign is negative. All right, so that's how we reduce that. This one is reduced as the cos of 73 degrees. Okay, but 180 plus 73 lands us in the third quadrant where cos is negative, so that will be negative cos of 73 degrees all squared. Don't forget the squares. So that will be 360 plus 180 plus 170. It will land us in the third quadrant, so that lands us with its negative sign is negative. There's the negative sign of 17 degrees all squared, which is equals to the cos of 73 can be written as 73 degrees will be 90 degrees minus an acute angle. To find the acute angle, we just go 90 minus 73, and that gives us 17 degrees. So we're getting there. It gives us 17 degrees. Wait, sorry about that, I made a mistake. So it's 17 degrees, so that will be negative minus cos of 90 degrees minus 17 degrees. Okay, that is all squared, plus negative sine of 17 degrees all squared. Okay, cos of 90 minus 17, that is sine of 17 degrees, so that leads us to minus sine of 17 degrees all squared plus negative sine of 17 degrees all squared, which is equals to negative a all squared plus negative a all squared. Now that gives us a squared plus a squared, which when we add together gives us 2a squared, and that's how you simplify this. That's how you simplify without a calculator. Next question. Question number 2 of this type is determine the value of the following without the use of a calculator. Whenever they say without the use of a calculator, you know you're going to need the cast diagram and the square and quotient identities just to help you navigate that. So let's start. 10 of 180 degrees, let's simplify that. That is equals to 180 minus x lands us in the second quadrant where 10 is negative, so that will be negative 10 of x. That's how we reduce that. And then we've got cos of 360 plus x. 360 plus x lands us in the first quadrant where every trigonometric ratio is positive, so that becomes cos of x when we reduce. So far so easy. Next, at the bottom we have 2 times cos of 90 degrees plus x. This will change into a cofunction, so that will be 2 times, let's put that in brackets, cos of 90 degrees plus x lands us in the second quadrant where cos originally is negative, so meaning that the cofunction it changes into, which is sine, will also be negative, so that will be minus sine of x. And therefore now the signs, the negative signs cancel out. Okay, let's cancel out the negative signs, and then the 10 is changed into its quotient identity, so it becomes sine of x over cos of x times cos of x. That you can also write as over 1 if you want to. No need to do that, but that's how you work it out. Okay, all over 2 sine of x, 2 times the sine of x. The cos's at the top cancel out. There we go, they cancel each other out, and that leaves us with sine x at the top. So that is sine x over 2 sine x. The sine x's cancel out. It goes once, and that leaves us with 1 over 2. And that is how you simplify that without a calculator. The third type is when you've got angles that will eventually turn into special angles that you can use the special angle triangles and the cast diagram to work out. So let's do that. Let's write all the compound angles in terms of a combination of angles, your special angles with the 180 or 90 or whatever the case may be. All right. So that is cos of 70 degrees. Let's leave it that way, cos it an acute angle for now, times cos of 135 is a compound angle. So, and it lands us in the second quadrant. It lands us in the second quadrant, and we know that in the second quadrant, we write our angles as 180 minus theta. So we need to find the acute angle that was subtracted from 180 in order to give us 135. And to find that, you just go 180 minus 135. It's up to you how you prefer to do that. You can work this out in many different ways. It's up to you. Whatever system you figure out, to use that as long as it works for you. 180 minus 135, that is equals to 45 degrees. So the acute angle that was subtracted here was 45 degrees. So we write cos of 135 as 180 degrees minus 45 degrees. And that's a special angle. We can use a special triangle to calculate. Next, at the bottom, we have sine of 150 degrees. 150 is a compound angle that lands us in the second quadrant. We need to express that as 180 minus an acute angle. So we go 180 minus 150. And the acute angle will be 30 degrees. So that is 180 minus 30 degrees. So that is sine of 180 minus 30 degrees. That's a special angle. 180 minus 30 degrees times. Next is sine of 160. That also lands us in the second quadrant. So that will be sine of, let's see, sine of 180 minus 160. 180 minus 160. It gives us 20 degrees. It's not a special angle. 180 minus 20 degrees. Minus 20 degrees. Okay, it's not a special angle. However, if you look at this, this is how you can also express it. Okay, you can express it like this, or you can express it like this, which is what I actually prefer. It does not give us a special angle when you express it in terms of 180. Let's try and see what special angle it gives us when you express it in terms of 90 degrees. So you go 160 minus 90 to see if we have a, there we go. So we get 70 degrees, which we already have that 70 degrees in a cos at the bottom. So that will be, let's express it as that. This way will also get you to the answer. So whichever way you prefer, there are many ways to kill this cat. You can use that way you like. You will also get to the correct answer. That is multiplied by sine of 225. 225 is in the third quadrant. All right, so that will be 180 plus the acute angle. 225, 180 plus. To find the acute angle, you subtract 180 from 225. 225 minus 180. That gives us 45 degrees. So that is 45 degrees. It's a special angle, so it will be easy to use to calculate. So that is multiplied by sine. Okay, let me just shift this a bit. The sine of 180 plus 45 degrees. All right, now that we've turned everything into special angles, let's go ahead and reduce. So that is cos of 70 degrees times cos of 180 minus 45. That's in the second quadrant where cos is negative. So that becomes negative cos of 45. Negative cos of 45 degrees. All over At the bottom, we have sine of 180 minus 30 degrees. It's in the second quadrant. Sine is positive there, so that reduces into the sine of 30 degrees. Sine of 30 degrees times the sine of 90 degrees plus 70. That lands us in the second quadrant, where originally sine is positive, and that changes into the cofunction, so that will be positive cos of 70 degrees, which matches with the one at the top. So we're good because they will quickly cancel each other out. 180 plus 45 degrees lands us in the third quadrant, where sine is negative, so that reduces to negative sine of 45 degrees. Negative sine of 45 degrees. Negative sine of 45 degrees. And now we cancel out what can be cancelled out. So we cancel out the cos of 70. There we go. And then the negative signs also. That leaves us with cos of 45 degrees over sine of cos of 45 degrees. These are special angles, so we can use the special triangles to calculate them without a calculator, which is the whole point. Sine of 30 degrees times the positive sine of 45 degrees. Now we go to the relevant special angles. So now the special angle of 30 degrees there. Okay, let's start with the 45 degrees. Cos of 45 degrees, this is the one. Cos of 45 is adjacent over hypotenuse, so that gives us 1 over square root of 2. So that is equals to 1 over square root of 2 times all over sine of 30 degrees. That will be opposite over hypotenuse. That's 1 over 2. 1 over 2 times the sine of 45 degrees is sine of 45 degrees. That's opposite over hypotenuse, so that's 1 over root 2. 1 over root 2. Okay, 1 over square root of 2, and that is equals to, so we go 1 over root 2 all over 1 over 2 root 2, and then you take this and you go 1 over root 2 multiplied by 2 root 2. You flip this one upside down over 1. The root 2's cancel out, and that leaves you with 2 over 1, which is simply equals to 2. You can use a calculator, but you're not supposed to use a calculator, and that's how you work it out. Next question, we're going to look at how to prove trigonometric identities. Now here is a simple way. Some tips on how to prove trigonometric identities. Number 1, you start from the complicated side and simplify until the simpler side. It could be the left-hand side, it could be the right-hand side that's complicated. You start with that and then simplify until you get to the simpler side. Number 2, you start from the left-hand side and simplify halfway, then start from the right-hand side and simplify halfway. The 2 will then be E. In this case, we've got the messy side is on the left-hand side, so let's start with the left-hand side. The left-hand side equals to 8 over sine squared of A minus 4 over 1 plus cos of A. Okay, that is equals to, so what you do is you notice that sine squared of A can be expressed as in terms of cos, and then you use the square identity for that. Sine squared is 1 minus cos squared of theta, so we express it in terms of that. So we can then use the factorization of the difference of two squares to factorize that. Now let's factorize this difference of two squares. That gives us 1 plus cos of A times 1 minus the cos of A. which makes it possible for us to find the lowest lowest common denominator, which has 1 plus cos of A, like you would when working with any set of fractions, common fractions. So the LCD is simply 1 plus cos of A times 1 minus cos of A. Now what we do is we multiply each one of the fractions by the LCD, which will give us, okay, first of all, we must have everything under the LCD. Right, there is the LCD. 1 plus cos of A times 1 minus cos of A. That is equals to, alright, so now we multiply this by the LCD like you would any, okay, so that's 8 over 1 plus cos of A times 1 minus cos of A, multiply by the LCD, which is 1 plus cos of A times 1 minus cos of A. All of these cancel out, so they all cancel out. You're left with 8 at the top. That's 8 minus, and then that will be 4 over 1 plus cos of A, multiplied by the LCD, and that results in 1 plus cos of A cancelling out with the other one, so that leaves you with 4 times cos of 1 minus cos of A. That's what we have there. So now that leaves us with, okay, let's simplify this. This becomes 4 minus 4. Okay, let's remove this. 4 minus 4. That's 4 minus 4. Okay, so that's 8 minus 4, sorry. 8 minus 4 plus cos of A all over the LCD, and the LCD is, okay, that's 4 cos A, sorry. 4 times cos of A. Make sure you don't make these silly mistakes here, because it could, yeah, that could change a lot of things. And then at the bottom we have 1 plus cos of A times 1 minus cos of A, which is equals to 8 minus 4 is 4 plus 4 cos of A. Notice that the numerator can already be factorized there. 1 plus cos of A times 1 minus cos of A, which is equals to, take out a common factor at the top, that's 4, leaves us with 1 plus cos of A, which you then simplify by cancelling out with the 1 at the bottom, and that's how you end up with the answer. That's, so this one cancels with this one, and you're left with 1. You're left with 4 over 1 minus cos of A, and that equals to the right hand side, and you've proven, which is equals to the right hand side. Mission accomplished. There we go. Next, this is the second example on how to solve the identity. So you're given this on the left hand side, and you're supposed to prove that it is equals to the right hand side. The left hand side is the messy one, so let's start there. So here is where we go. We go therefore the left hand side equals to sine of theta minus 2 sine of theta cos of theta. You can already see a common factor you can take out over there. Okay, and then at the bottom we've got 2 cos squared theta plus cos of theta minus 1. Now notice that this one is a trinomial, which is called a quadratic trinomial. There, it's like your x squared, 2x squared. If you were to replace cos with k, for example, that will be 2k squared plus cos plus k minus 1. You see, now this one becomes very easy to factorize. Become 2k and k with 1 and 1, and then plus 2 minus 1. That's how we're going to factorize that. So this is a trigonometric, a quadratic, no sorry, it's a trigonometric quadratic situation there. So let's take out a common factor over here. That's sine of theta. Then it leaves us with 1 minus 2 cos of theta. All over. Let's factorize the quadratic trinomial at the bottom. So that will be 2 cos of theta, 1 and 1 plus and minus according to this. Now that gives us what? Okay, so you can see the denominator 2 cos of theta minus 1 is almost similar to this one. So what we do is we put a minus in front of this one at the top, so we can rearrange that into something similar with the denominator, so that becomes 2 cos theta minus 1. That's what the effect of the minus in front of that gives us. So that's 2 cos theta minus 1, 2 cos theta minus 1 times cos of theta plus 1. These ones cancel out, and that leaves you with negative sine of theta plus cos, and that's exactly what we started with. So that leaves us with negative sine of theta all over cos of theta plus 1, which is equal to the right hand side, and there it is. It equals to the right hand side, and that's how you do it. You manipulate until you get to where you want to go. So we've proven that identity. Next, for which values of theta will the identity be undefined? That's very easy. For which values of theta? Anything that we divided by, there is what we divided by. So that will be cos of theta plus 1 and 2 cos of theta minus 1. So 5.2.2 the denominator cannot be 0, so whatever will make things undefined is if the denominator is undefined when the denominator is 0, meaning when 2 cos squared theta plus cos of theta minus 1, when that is equal to 0, meaning that when the factors 2 cos theta minus 1 and then the cos of theta plus 1, when this is 0, meaning the factors, or if cos of theta plus 1 is equals to 0. So now let's solve this mini trigonometric equations. So therefore that gives us 2 cos of theta equals to positive 1 on the left hand side, which leaves us with the cos of theta equals to 2 a half. Now therefore, okay, to find the angle, theta will be equals to cos to the minus 1 of 1 over 2, which is equals to what? Take out the calculator, shift cos common fraction 1 over 2 equals to, it gives us 60 degrees. So that's 60 degrees plus k times 360 degrees if you want. So therefore cannot be plus k times 360 degrees. In other words, you can go as many revolutions as you want, but if it lands you in that 60 degrees, or then it will be undefined. Or what? Okay, when cos of theta, this one, cos of theta equals to negative 1. All right, when is cos of theta negative 1? Therefore, it means that theta equals to cos of negative 1 to the minus 1, which gives us what angle? Let's see. Shift cos of, all right, let's go. Shift, then the cos of negative 1. That gives us 180 degrees. And we'll go the plus k times 360 degrees. So therefore, the identity is undefined for when k. Therefore, the identity is undefined. Undefined when, please excuse the noise, when your angle theta is equals to 60 degrees plus k times 360 degrees, if you understand, or when theta equals to 180 degrees plus k times 360 degrees. That just means as many revolutions both in the positive and the negative direction of the cast diagram, where k is an element of integers. We're going to focus on this more in the next video, where we look at trigonometric equations. Come to the end of this video. Thank you so much for watching. I'll